Warm greetings. I am Dr. Shitanshu Shekhar Chakraborty, working as a scientist at CSIR Central Mechanical Engineering Research Institute. The title of the project, funded by Science and Engineering Research Board under Early Career Research Award Scheme, was Laser Forming of Aluminium Foam Plate to Produce Curved Surfaces. Aluminium foam and actually metal foams have wide applications including energy absorption, mechanical damping, vibration control, acoustic absorption, heat exchanger and lightweight structure. But these materials are difficult to form mechanically because they lack the tensile strength, and at the bottom where there is high tension, it tends to fracture. Also in foam sandwiches there are other failure modes like core failure or penetration of the top sheet onto the core or delamination, etc. Thermal forming can come to rescue and laser, when used for thermal forming, the process is called laser forming. 3 different mechanisms have been reported for laser forming, like temperature gradient mechanism, upsetting mechanism and buckling mechanism. So in temperature gradient mechanism, when the Fourier number is less than 1, the beam irradiates or heats up a small depth up to small depth from the top surface. This heated region tries to expand and is resisted by cold bottom layers. Therefore upon cooling, the sheet bends towards the laser beam. If the Fourier number is greater than 1 and the beam diameter is of the order of sheet thickness, there is very less gradient through thickness. The entire irradiated or entire heated region tries to laterally expand and is resisted and compressed by the bottom by the cold lateral sides. Under similar heating conditions, when the beam diameter is of the order of 10 times of the sheet thickness, there is a buckling. These are the approved objectives. We have to do the numerical and experimental analysis on laser forming of aluminium foam and foam sandwiches, and also we have to demonstrate the process capability by laser forming a practical automotive part. So aluminium SiC composite closed shell foams, pure aluminium 95% porous foams and aluminium foam sandwich was used as materials. Bending angles were measured with the help of laser displacement sensor mounted on translation stages, and the bending angle was measured based on laser triangulation method. There were 3 different approaches of modeling the foam geometry in simulation. One is equivalent solid model, where the properties determined based on scaling law were given, and the entire foam was considered to be an equivalent solid model. In cellular model, the average pore size is distributed throughout the model and solid material properties are given. And in voxel model, the CT scan based geometric model constructed based on CT scan are used and the solid material properties are given. We had used a different cellular models where, similar to the face-centered cubic crystal, instead of atoms, the voids were placed at the positions corner at the face centers, and they were separated by average strut wall size obtained through CT scans, and at the body center position half a size of the void was placed to mimic the entire porosity of the foam, and this unit was repeated to create the cellular model. The other assumptions included temperature dependent properties and the radiation and convection and intensity distribution of the laser beam as Gaussian, and also the sequentially coupled thermomechanical analysis were used, where transient thermal analysis is first solved and the temperature distribution thus obtained is given as a predefined field in the subsequent mechanical analysis. When we used the porosity as an independent variable, we could improve the lack of fit, etc. could be reduced, and the experimental results became significant. Okay, so apart from laser power, scan speed and beam diameter, the density or relative density was used as another factor. So out of the three models, that is equivalent solid model, cellular model and the voxel model, the cellular model gave the best prediction of bending angle, and or that too consuming the least amount of time. In the experimental results on open cell foams, there were some interesting observations. In laser forming of sheet metals, the bending angle per scan pass tends to reduce with increasing number of scan pass. However, that did not happen in case of open cell foams, because due to the cell densification, the laser energy coupling was increased, and that could offset the effect of section thickening, strain hardening, and reduction in laser fluence. Same thing also could explain the higher bending angle in case of higher scan path curvature. With increase in thickness, the bending angle reduced, and with distance of the scan path from the clamped end, the bending angle increased as the path were close to the beam, the clamped end. So this work was reported in Journal of Laser Applications and was selected as a feature article. So the final part was demonstration of process capability by forming an automotive part. A scaled down model of a bumper beam was chosen based on material availability and also the capability of the workstation or the size limitation of the workstation. However, the radius of curvature was kept same as the original part. How to place the so since the part can be treated or formed as a developable surfaces, a sequence of bending angles, scan lines, bending through a sequence of scan lines could produce the part. Only production of half portion of the part is explained here. How now you can place a scan line at certain length of the curved path, and you have to impart a bending angle, which is the difference in bending angle subtended by that curved part and the total bending angle subtended at the center. So that difference has to be imparted by that scan lines. Similarly, you can go on placing scan lines and obtain the angle to be imparted by them. The final angle that will be remaining from the total angle will be shared by the last two lines, which will be close to the central clamp. With that, we could obtain the required bending angle for each scan path. Now, what will be the number of irradiations to impart that required bending angle with certain optimum laser parameter combinations? For that, we need this experimental database. So we could form the scale down model of the bumper beam, and through 3-point bending test, we could show that there were no loss of compressibility or energy absorption capability after laser forming. So these were the journal papers and one book chapter in Spinger, lecture notes in mechanical engineering. These are the equipments procured. I sincerely thank SERB to fund this project under grant number ECR 2017-002505. Thank you.